Hey everyone, Miss Name here with a short video. Let's work through this practice quiz together. The first question gives me a function y, or I could say f of x, equals 4x plus 4 over 1 minus x squared. We want to graph and sketch it. So let's rewrite it over here, but I'm going to go ahead and factor it right away. On the bottom, I'm noticing that these are not in descending order, so I'm going to rewrite it so that it follows convention. X squared in the front, constants at the end. Okay, so notice we have this negative in front. Let's factor that out as well. So that flips my x squared to be positive, and my 1 will become negative. And by taking that negative out, which by the way is a crucial step that many people forget to do. If there's a negative in front, you have to pull it out. Once we do that, we can see there's an opportunity for a difference of squares. So really, this factors to negative x minus 1 and x plus 1. Once I've factored it all the way, look for opportunities to cancel expressions. I have an x plus 1 and an x plus 1 that can be canceled, meaning that I found a whole. So my whole is at the root of the canceled expression. So the root of x plus 1 is x equals negative 1. That's where my whole is. So to find the y value, if that's the x value, then to find the y value of my whole, I'm simply going to plug this negative 1 back in to the reduced expression. So when x is negative 1, I'll write it like this, f of negative 1 to show that I'm plugging in x. Then we get 4 over, so we've canceled out the x plus 1s, so we're 4 over negative parentheses, negative 1 minus 1. And again, we canceled the x plus 1, so we're not going to include it. So that gives me 4 over negative 2, which is 4 over positive 2. 4 divided by 2 is 2. So nice, we found out not only where our whole occurs, but also the y value by plugging that x back in. So at negative 1, 2, we have a whole. Okay, let's move on to the next piece. We want to find the vertical asymptote. So let's rewrite our reduced function, and we're going to use our reduced function for the rest of the problem, which is y equals negative 4 over negative x minus 1. When we say reduced, it means we've canceled everything that could be canceled. Oh, sorry, that's not a negative 4. That's just a regular 4. So my vertical asymptotes, I know that they come from the bottom, and it will be the root of the denominator. So my vertical asymptote will occur at x equals positive 1, the root of that expression. My horizontal asymptote comes from looking at the degree on the top and the degree on the bottom. On the bottom, I can see that the highest power is 1. If I multiplied this all out, I would get negative x plus 1. And so clearly, our highest power on the bottom is 1. On the top, there's no x at all. So if you think about it, it could be x to the 0. Either way you look at it, the bottom has the higher power for x. Since this is bottom heavy, we have an asymptote at y equals 0 for our horizontal asymptote. So let's draw those in. Our vertical asymptote is at 1, and our horizontal asymptote is at 0. We looked at the degrees, and this was a bottom-heavy graph. And now for the y-intercept, I know I simply set my x's equal to 0. So when x is 0, the question is, what's the y value? Well, let's plug it in. We have 4 over negative 0 minus 1, which gives me 4 over negative 1, which gives me 4 over positive 1, which is just 4. So my y-intercept occurs at 0, 4. Notice I'm putting a closed dot to show that I'm actually going through the point and an open dot at my whole. So from that much information, I can tell that my graph needs to go through these points and it's going to go up and get closer and closer to my asymptote. Then it's going to come down and get closer and closer to my asymptote. There's no other way it could go. It can't go like this because that would be crossing the x-axis, and there's no x-intercept there. Okay, and it can't go like this because we know it has to get closer to the asymptote. So it's got to hug the asymptotes. Now you might be wondering, well, what about this side of the graph? We need to figure out where the function is, whether it's above, it could look like that, or if it's below, it could look like that. So to figure that out, let's just plug in any point that is in this region. So x, let's plug in maybe 2, we could plug in 3, we could plug in 4, we could really plug in anything that's bigger than 1. We can't plug in 1 though, because if I plug in x equals 1, I'm going to get does not exist, because we know that we have an asymptote there. So let's plug in some number to the right. Let's plug in 2. So let's see, what's f of 2? Well, again, we're using our reduced function. We have 4 over negative 2 minus 1, which is 4 over negative 1, because 2 minus 1 is 1, and then there's a negative, and that's negative 4. So I found that I have a point at 2, negative 4. And so that's enough for me to realize my graph's going to look like this. All right, let's continue on. Oh, let's answer the domain question. So the domain is all the values, the x values where the graph exists. I'll highlight in orange. So the graph exists from negative infinity for all those x values until negative 1. It doesn't exist at negative 1 because of that hole there. So we got to exclude that from our domain. Then it exists again between negative 1 and 1. It doesn't exist at 1 because of the vertical asymptote. Then it exists again from 1 onwards to infinity. So in interval notation, we would say negative infinity to negative 1, negative 1 to 1, and 1 to infinity. Let's move on to the matching parts. Okay, so let's look at number 1. Actually, why don't we do this? Let's look at the graphs first. That might be easier. So from graph A, I realize I have a vertical asymptote at x equals negative 2. From graph B, I can see I have 2 vertical asymptotes. One at x equals negative 2, because I can tell since the graphs are kind of going up and down, but they're not hitting that line. And then also it looks like at x equals 1, we can safely say there's a vertical asymptote. For C, it looks like we again only have 1 vertical asymptote at x equals negative 2. So the difference between A and C then is that A also happens to have a hole. It's the only one with a hole at x equals 2. So just with that information, let's see if we can narrow this down. So I know vertical asymptotes come from the denominator, so let's examine these denominators. Here we got 2. For number 1, let's reorder this. So taking the negative, let's put these in order. Negative x squared minus x plus 2. Let's factor out the negative. And then let's factor it even more. So we can see that our first graph actually changes to 2x squared plus 5 over negative x plus 2 and x minus 1. So far, it seems like this might be the one that links to graph B. Why? Because the denominator gives me vertical asymptotes at 1 and at negative 2. But let's check the next one before we jump to conclusions. Okay, so those would be our vertical asymptotes. Let's look at number 2. Number 2, the top doesn't factor. The bottom doesn't factor. So number 2 only has a vertical asymptote at x equals negative 2. There's no holes or anything. Let's make a note, no holes. And then for number 3, you can start probably at this point figuring out all 3 of them, which go with which. But number 3, we have x minus 2 on top, and the bottom becomes a difference of squares, and we have x minus 2 over x plus 2. So number 3 is the only one, boop, boop, that leaves us with a whole at x equals positive 2, the root of the canceled expression. It also has a vertical asymptote at negative 2, since that's left in the denominator, the root of x plus 2. So with that information, we can confidently say that 3 represents graph A. Why? It has a vertical asymptote, and it has the whole, something canceled. Then 2 has got to be graph C, because it only has one vertical asymptote, and there's no holes. And then graph 1 has to be for B, since there was 2 vertical asymptotes and they matched up. By the way, you can't factor the top because it's a sum of squares, so we know for sure nothing will cancel. All right, let's do number 3 and we'll be done.